Hello everyone. In this video, let us see different expressions to calculate work done. We know that work done is nothing but product of force and displacement. Work done is equals to force into displacement. This work done mainly depends upon magnitude of force and displacement. The different possibilities are as follows. What are the different possibilities? Let us see. First possibility is both force and displacement are in same direction. Both force and displacement are in same direction. Force is a vector and displacement is also a vector, right? Second possibility is both force and displacement are in opposite direction. And third possibility is the direction of force makes an angle with the direction of displacement. And fourth possibility is work done against gravity. Let us see different expressions to calculate work in these four different possibilities. Let us take first possibility A. Work done when force and displacement are in the same direction. Are in the same direction. Consider a body at point A. Let us take a body here. This body is at point A, right? It reaches the point B. Let us consider another point here. This body is reaching point B. When a force F is applied, so here a force F is exerted on the body such that the displacement of the body is in the direction of force. This is the displacement of the body. Displacement is S. In which direction it is? In the direction of force. This is the displacement and this displacement is in the direction of force. The expression to calculate work done is, right? Work done is equals to force F into displacement S. Then I can write this W is equals to F into S. This is the expression for work done, right? When this is the expression for work done, when force and displacement are in the same direction. Here force and displacement are in the same direction, right? Now let us see some important points. Let us take note related to it. Note. First important point in this note is this formula. When we have to use W is equals to F into S, direction of force and displacement are the same. Direction of force and displacement are the same. Then only we have to use this formula, this expression W is equals to F into S. And second important point is the work done by a body is zero. Work done by the body is zero, right? If force is acting, if force is acting and displacement is zero, and displacement is zero, right? For this example is a person is pushing a wall. The person is exerting force on the wall, but the displacement of the wall is zero. Then work done by that person on the wall is zero. Third point in the note is as direction of displacement, as direction of displacement and direction of force and direction of force are the same, so work done is positive. Work done is said to be positive. Said to be positive. This is very, very important, children. Let me highlight this. Here, work done is positive. When it is positive, the direction of force and direction of displacement are same. Then the expression is W is equals to F into S, right? If we consider some examples for this particular condition, when direction of force and displacement are same, let us take first example. In villages, children are fascinated and interested to play games using marbles. In one of the games, they use their thumb and index finger to move the marbles. Here, the work done by the index finger as the force applied by it displaces the marble through some distance in the direction of the force. Here, work done is positive, and we can use expression W is equals to F into S. Second example, when a shot is fired, the force of pressure of gunpowder does the work. It shifts the bullet along the barrel with an increasing speed. In this, the direction of force and displacement of the shot are in the same direction. A man playing snookers with the cue. Cricket batsman playing straight drive. These are some of the examples where work done is positive and expression used is W is equals to F into S. Now let us see second possibility, that is B. Work done when the force and displacement are in opposite direction. Right. Let us see expression for this. When work is done when the force, direction of force and displacement are in opposite direction. Let us consider a moving car. Let me take a car, right? A car which is moving, right? This car is moving. Let us consider the direction of the car. Consider a moving car, right? Try to stop the car by applying some force F, right? Car is moving in this direction. We are applying some force over this car to stop this car. We observe that the car comes to rest after traveling some distance, right? It travels some distance and it comes to rest. How to stop this car? By applying force. We apply force on brakes to stop the car. And this force is exerted in the direction opposite to the direction of motion of the car, right? And therefore, the displacement is taken as negative. Here the displacement can be taken as negative because force is exerted. The direction of force is opposite to the direction of motion of the car. Then I can write here work done is equals to force acting, that is F, into displacement. Displacement, that is S, right? Here force acting is F into displacement is minus S, that is work done. Okay, so then I can write this as W is equals to minus Fs. This is the expression for work done when force is the direction of force and the direction of displacement are opposite to each other, right? Let us consider a note here, right? Note, as the direction of displacement and direction of force are opposite to each other, work done is said to be negative. Direction of force and displacement are opposite, right? So work done is said to be is said to be negative. Earlier work done was positive. Here work done is negative because direction is opposite. Their direction is same, right? Right? Now let us consider some examples for this, where work done is negative. A man moving upwards on the stairs, right? Applying brakes of a moving motor vehicle. Rowing a boat on the surface of the water. An elevator moving upwards in a building. In all such cases, force exerted opposite to the direction of motion of the body. Now let us see third possibility, where the expression of work done is different. Third possibility, that is C. Work done by a force. Work done by a force that makes an angle with the direction of displacement. Right? So If we see second possibility, here let us highlight this. Here, work done when the force and displacement are in opposite direction. Then the expression is W is equals to minus Fs and work done is negative, right? Now we have seen next possibility, that is fourth possibility. Third possibility, that is work done by a force that makes an angle with the direction of displacement. We have seen that whenever work is done, a body displaces in the direction or opposite to the direction of force applied. But in some cases, the body moves in a direction that makes an angle with the direction of displacement. For example, when a child pulls a toy car using a string attached to it, the car moves horizontally on the ground, but the force applied by the child is along the string held in his hand, making an angle with the direction of displacement of the body, which is horizontal to the surface of the ground. Let's see in the diagram. Here, the toy car moves along the horizontal ground surface OX, but the force is along the string OA. Thus, the direction of force makes an angle theta with the horizontal. In such cases, we cannot use W is equals to F into S to calculate work done, as the displacement S is not exactly in the direction of force applied. Therefore, we need to know the magnitude of force in the direction of motion of the body. Let us try to find the magnitude of force that acts horizontally. Force is a vector quantity, as we know that, and makes some angle with the horizontal. This force can be resolved into two components as shown in the figure. One component along the direction in which body moves, which is called horizontal component, that is represented as FH. What is that component called? Horizontal component. Horizontal component, which is represented as FH. And another component acting perpendicular to the horizontal, that is vertically upwards, called vertical component. Second is vertical component, that is F subscript V. And this force F is resultant of horizontal and vertical component, which is making an angle theta with the horizontal component. The work is done only by the horizontal component of force, as the body moves in the horizontal direction, right? Now, if you observe this figure, right, here the angle is theta, FH is horizontal component, F is resultant force, and FV is vertical component, right? Now, we can express it as FH can be expressed in terms of F and theta. What is F? Resultant force F, and theta is the angle between horizontal component of force and the resultant force, right? So let us use here cos theta, right? We know that from the definition of cos theta is nothing but here adjacent side by hypotenuse. Theta is this, and this is the opposite side. This is adjacent side, and this is hypotenuse. OX is adjacent side, XA is opposite side, OA is hypotenuse, right? From the figure, we can write cos theta is equals to adjacent side upon hypotenuse. So what is adjacent side? OX. Hypotenuse is OA, right? OX is nothing but here F, horizontal component FH. O is nothing but hypotenuse, that is force F, right? Then I can write this cos theta is equals to FH upon F, right? I want horizontal component. FH is equals to F cos theta, right? Here, work done is measured as product of magnitude of component of force along the direction of displacement and magnitude of displacement. So I can write work done is equals to magnitude of component of force into displacement of the body, So I can write this W is equals to, that is work done, W is equals to horizontal component is F cos theta, that is FH is nothing but here F cos theta into S. Therefore, work done W is equals to F S cos theta. This is the required expression for work done, right? When force is making an angle with the displacement of the body. So this is the expression that is used when work done by force that makes an angle with the direction of displacement. Here, let us take a note for this possibility. Note. Okay, we have angles for cos here. We know that cos 0 degrees is nothing but here 1. Cos 30 degrees, it's nothing but root 3 by 2. Cos 45 degrees, it's nothing but 1 upon root 2. Cos 60 degrees is equals to 1 by 2. And cos 90 degrees is equals to 0. So this is third possibility where expression of work done is W is equals to Fs cos theta. Now let us see the fourth possibility, that is D, work done against gravity. Work done against gravity. Let us see this fourth possibility. Consider a book or an object lifted from a table. We do work against the force of gravity. Whenever work is done against gravity, the force required to lift the body is equal to its weight. Therefore, the amount of work done is equal to the product of weight of the body and the vertical distance through which the body is lifted. Let us take an example here. This is an object which is over a surface. This is the surface on which this body is placed, right? Now this body is lifted to a height h. This is the height h to which this body is lifted when it is placed over the surface, right? Then here work done is equals to work done, W is equals to, in lifting this body, that is equal to weight of the body. What it is? Weight of the body weight of the body into vertical distance. Vertical distance. Right? We know that work done is nothing but W, that is weight of the body is nothing but mass into acceleration due to gravity, that is mg, m into g, and vertical distance is nothing but the height to which the body is lifted into h. W is equals to mgh. But when work is done against gravity, then W is equals to minus mgh. This is the expression for work done when work is done against gravity. Work done against gravity. Right? Let's see note related to this possibility. When work is done against gravity, acceleration due to gravity is taken as negative. Is taken as negative. Yes, acceleration due to gravity is taken as negative when work is done against gravity, right? But the magnitude of work, the magnitude of work is always positive, is always positive. Examples for work done against gravity is when a suitcase is lifted from the ground to some height, right? And when a ball is thrown vertically in the upward direction are some of the examples for work done against gravity. Hope you have understood all the possibilities for work done and their expressions. Thank you.